In this lesson, we are going to recall midpoint and distance formula, equation of a circle, and we are going to graph various functions. If we have 2 points, for example this P and Q, with general coordinates x1, y1, x2, y2, then the midpoint of the line segment PQ has coordinates that are actually the averages of the coordinates of the 2 points. How come? Well, to justify this formula, we can look at the diagram and complete the right angle triangle by projecting point P and Q perpendicularly with the segment PQ as hypotenuse. Assume that M is our midpoint, therefore the distance PM is exactly half of the distance PQ. And if we project point M vertically and horizontally onto the sides of the original right angle triangle and mark those projections, for example, as MX and MY, let's also mark the vertex of this right angle triangle as C, then the x-coordinate of point M is the same as x-coordinate of a point MX, which is somewhere here. So we see lots of similar triangles here, for example this small one and the big one. So using similar triangles properties, we know that the ratios of corresponding sides are preserved. So for example, PM over PQ is 1/2, but it's also equal PMX over PC. That really tells us that this segment PMX is actually half of PC, which justifies that the coordinate of the MX point is exactly the average of the coordinates of P and C. Since the x-coordinate of P is x1 and the x-coordinate of C is x2, therefore the x-coordinate of MX is an average x1 plus x2 half. Similarly, we can justify that the y-coordinate of a point MY is the average of the y-coordinates of these 2 points, Q and C. y1 is here and y2 is over there. As we see, this point is your y1 plus y2 over 2, average of the y-coordinates. So that's the formula for midpoint. To develop a formula for the distance between P and Q, we'll start with Pythagorean theorem, which says that the sum of squares of the 2 sides of the right angle triangle is equal to the square of the diagonal. So if I call the distance PQ by D, then the distance PC can be expressed in terms of x-coordinates of points P and Q. So it is x2 minus x1, and the distance CQ can be expressed in terms of y-coordinates, y2 minus y1. So we can write Pythagorean equation d square equals the difference in x-coordinate square over here plus the difference of y-coordinates square. From that equation is just one more step. We need to solve for d by taking square root on both sides, and we end up with the distance formula. So d is square root of the sum of squares of the difference of x and y coordinates. And we have one example to go through. Find the midpoint and the length of the line segment connecting points A and B with given coordinates. So let the midpoint be called M as before. Therefore the coordinates of M should be the averages of the x and y coordinates. So we go 4 plus -2 over 2 and -3 plus 7 over 2. Now it's enough to simplify, so we have 2 over 2, which is 1. And here we have 4 over 2, which is 2. So the midpoint of this line segment AB has coordinates 1 and 2. Now to find out distance AB, we follow the second formula, we take square root of the sum of squares of differences between coordinates. So 4 minus negative 2, which is really 4 plus 2. And here we have negative 3 minus 7, so it's really negative 10. So altogether we have root of 6 squared is 36 plus 100, meaning root of 136. Now we could simplify this root of 136 by factoring on the side 136 using factor 3. That will be 2 times 68, which factors into 2 times 34, which factors even further as 2 times 17. So we can actually pull the 2 out of the root, leaving 34 under the root. So this will be the distance, 2 root 34. We just developed the formula for a distance. What if we wish to find the set of points that are equidistant from a specific point? Like for example on this picture, all the hands of those people are at the same distance from certain central point that will be called a center. We know very well this shape. This is a circle. If we look at all those heads, they are also at the same distance from the central point, except that this time the distance is a little bit farther. So the distance from the center to any point on the edge of the circle is called radius. Here's a small radius, here's a little bit longer radius. Let's call it capital R. Formally, a circle is a set of points in a plane that are at certain distance r from a fixed point O, usually called a center, and the distance r will be called the radius of the circle. How can we develop an equation of a circle with the given center, with, for example, coordinates hk, and the given radius, called r? Well, we follow exactly the definition of what the circle is. If I have any arbitrary point xy that belongs to the circle, its coordinates xy must satisfy the condition that the distance between these 2 points is constantly the same and it's equal to r. So what's the distance between hk and xy? Well, this is the square root of x minus h square plus y minus k square, and it's equal to r. If we don't like to have the square root, we can square both sides and we end up with x minus h square plus y minus k square equals r square. And this equation will be our standard form of an equation of a circle. So equation of a circle has this form. Let's highlight it. And notice that from such equation it's very easy to rate the center just by taking the numbers h and k with opposite signs. So center has coordinates h and k, and the radius is the number under the square. Here we have example how to find an equation of a circle if we have a graph given. Well, from this graph we can easily rate the center. Center has coordinates negative 2, 3, so we have the h and k. And the radius. The radius is from the center to some point on the circle. We have this point D given, so we can find out the distance CD. This will be our radius. So CD is square root of difference in x coordinates, 4 minus negative 2, which is 4 plus 2 square, plus 5 minus 3 square, and when calculated, this is square root of 6 square 36 plus 2 square, which is 4. So we have square root of 40, which could be simplified if needed to 2 root 10. Now we can use the radius in the center and plug it into the equation of a circle in standard form. So we have x minus -2, so it's plus 2 square, plus y minus 3 square. It's supposed to be equal r square, but notice that since I need r square, it's even easier to take this value and square it. It will give me directly 40. So that will be the equation of this particular graph. In the next problem, we have given equation of a circle, except that it is given in a general form. So we don't have this completed square with x's and with y's. We have some x squares and some single x's, some y squares and some single y's. The question asks us to convert the equation to the standard form of a circle. So we really need to complete the square for x coordinates. How would we do it? Well, let's take the x, take the same sign as by 8x, so it's plus, complete the square, and the number that you take in a bracket is half of this middle coefficient 8, which is 4. Now, since we've done a little bit more than we had, because when you square it, you end up with x squared plus 8x, but you also end up with plus 16 that wasn't before. So that's why we subtract this perfect square of the number that is taken in the bracket. Next, we will look at y coordinates. So we need to complete the square for these two terms. Again, use a perfect square bracket, use y, the same sign as by the linear term, so it's -5. And then, since we have more than we had originally, we have to subtract perfect square of the number that we took in the bracket, so it's -25. And copy whatever's left, plus 37. So now what's left to do is to put together all the constant numbers and bring it to the other side. X plus 4 square plus y minus 5 square equals -16 and -25 is -41. On the other side will be +41, and 37 to the other side -37. So altogether we have just 4. Therefore we can write in the final answer first bracket square, second bracket square equals 4. Okay. So now we can answer the last part of this question. Find the center and the radius of this circle and then graph it. What's the center? Well, the center can be read directly from those brackets. So we have -4 and 5. And the radius is the square root of this free number here. So it's 2. Remember that in the formula this part is really r squared. So r by itself is just 2. Now we're ready to graph. Center -4, 5. -4 is, let's say, here. 5 is over there. So the center will be here. And radius 2. So what you do, you go 2 steps forward, 2 steps backwards, 2 steps up and 2 steps down. And then try to join as smoothly as you can these 4 points. And we have a circle. In the next section of this lesson, we're going to graph solutions of various equations. What we need to keep in mind is basic shape of the curve that we graph. That always helps. If we know how to recognize basic shape, what to expect as a final graph, then we're looking at x and y intercepts. Well, let's recall, to find out x-intercept, we set up y equals 0 and solve for x. To find out y-intercept, we set up x equals 0 and solve for y. And after that, check for possible additional points if still needed. So let's see some examples. Graph solutions to the following equations. The first equation, as you can recognize, it's a linear equation. And we know very well how to graph a linear equation. We can do it in 3 different ways. We can use table of values, something for x, something for y, and check 2 or 3 points. We can convert this equation to slope y-intercept by solving for y and then follow the slope y-intercept method. Or in the standard form as it is, we could use a combination of this table of values and x and y intercepts. This method should help us to graph very quickly. For example, if I use x equals 0, then this term is 0, and it's easy to solve in your mind that y equals 6 divided by -3, so it's -2. And if y is 0, this term disappears, so x would be 6 divided by 2, so it's 3. Then you plot your 0, -2, and 3, 0, and then just join these 2 points. You can develop in the same pattern 2, 3 to the left to make more points and be more exact. And then take a ruler and draw it as neatly as you can. Remember that when you graph any function, you must indicate some sort of scale on each axis by placing at least one number corresponding to a point on x and y axis. So for example, this point has coordinate 3 and that one has coordinate -2 on my scale. It's always a good idea to label points that seems to be important for the function. The next equation represents absolute value function. How do we graph this? Well, we can graph it in 2 different ways, either by using table of values or by transforming a well-known shape of related function, absolute value of x, and maybe list the transformation so we can see what's going on. How absolute value of x looks like? Well, that's a V shape like this. Now, to obtain a graph of a function that is a little bit closer to the desired one, for example, x plus 1, what kind of transformation do I need to perform from here to there? Well, if I add something to x inside the function, then I'm actually moving the original graph one step to the left. So this is translation by the vector -1, 0. Okay, therefore my point 0, 0 travels one step to the left. Point 1, 1 travels one step to the left, and so on and so forth. So the whole shape will become a V, but shifted one step to the left. This is not my final graph yet, but it's very close. The next step would be to drop everything by 2 down. So we have whatever we had before, -2. So what transformation works on the green graph to get the blue graph? Well, it's a translation by the vector 0, -2. We drop every single point 2 steps down. So the final graph will be still a V shape, but with vertex at the point -1, -2. So this is -1, this is -2 over here. Notice that these 2 transformations, from the yellow to the green and from green to the blue, could be replaced by one transformation, a purple one, just by translation by the vector combination of these 2, so -1 and -2. Those are the coordinates of the vertex. So that's the same as just moving the original vertex to the right spot and then drawing the regular shape starting from that vertex. We could also label these 2 points. Those are the x-intercepts. So that's 1 and -3. Now the y-intercept is -1. Here we have another very well-known shape. That's a parabola. So we know how parabola looks like. It must be this kind of shape or the upside down one. In this case, because the leading coefficient is positive, it is a parabola with arms up. And the vertex of this parabola we can rate as before by taking the first coordinate, a number that is in a bracket with opposite sign, so it's 1, and the second coordinate, a number that is outside of the bracket, which is -3. Now if I plot this point 1, -3, 1 here, -3 over there, and I know that the arms are up and the shape of the parabola is the standard parabola like x squared, because we don't have any coefficient before the bracket square, then I'm ready to graph it. Because in a standard parabola I go 1 across 1 up and 2 across 4 up, because 2 squared is 4. And then join these points. So here the y-intercept is easy to discover, that's -2. However, the x-intercepts are not so obvious. We could calculate this if needed by replacing y equals 0 and calculating for x. But at that moment we don't really need them, so let's leave it as it is. The following graph we can recognize as a graph of a circle. That's a standard form of a circle. So let's read information about the circle. The center has coordinates -1 and 2, opposite to the signs that you see, and the radius is a square root of that number, so it's 3. So -1, 2 is here. Radius 3 means 3 steps across horizontally and vertically. And then try to join them as neatly as you can to draw a full circle. Again, the x and y intercepts are not very nice numbers, but they can be calculated from the original equation. Here we have another absolute value shape, but this time something strange happens, because x is equal to some function of y, rather than y as a function of x. So to discover what's going on with this shape, maybe it's a good idea to draw a table of values and check some values for x and y that will satisfy this equation. For example, if x is 0, then my absolute value of y would have to be 2, which means that y by itself could be either 2 or -2. So we have actually two values that are attached to 0, either 2 or -2. These 2 points belongs to the graph, which really means that this graph won't be a graph of a function. It won't satisfy the vertical line test. Similarly, as the previous circle wasn't a function, it was just a relation. But that's okay, we can still graph it. So let's choose some other points. If y is 0, then x is -2. So this way we have all intercepts. If x is -2, y is 0, so it's this point. Well, it must be some sort of V-shape because we have absolute value. My intuition tells me that this V-shape will be somehow like this. But let's check a couple more points. So if y is, for example, 1 or -1, since both 1 and -1 result in the same absolute value, so 1 minus 2 will give me -1 for x. So I have 2 more points to plot. -1, 1 and -1, -1. Oh, it looks like it will be this kind of V-shape. Let's check one more point. Let's say if y is equal to 3 or -3, then the x is 1 for both. So 1, 3 and 1, -3. Now we are pretty sure that the graph will be a sideways V-shape, like this. So we have x-intercept -2 and y-intercept -2 and 2. And this is a relation but not a function. Here we most likely have another relation. Why? Because for every x, I can actually come up with 2 possible values y that will result in the same absolute value. So let's use table of values, x and y. If x and y are positive, how can I create 5? Well, I can use 0 for x and 5 for y. But y, it doesn't matter if it's 5 or -5, the absolute value will still give me 5. So I have at once another point, 0 and -5. Now, starting with positive x and y again, to create 5, you can go by 1 and 4. And similarly, -1 and -4, because absolute value of each of them will result in the same number. Also, -1 and 4 and 1 and negative 4, so all possible distribution of signs will work. Next we can try 2 and 3, or 3 and 2, or 4 and 1, or finally 5 and 0. So maybe two more. Let's say if I have x3 and y2 and all the possible combination of signs, I could have x4 and y1 and all possible combination of signs. And finally, I could have 5 on x and 0 on y, still with different signs. So let's plot those points. 0, 5 and 0, negative 5 are those extreme points. Then 1, 4, 1, negative 4, negative 1, 4, and negative 1, negative 4. Similarly with 3 and 2, at negative 3 and 2, this one and that one. And finally 4 and 1, 4, negative 1, and negative 4, 1, negative 4, negative 1, 5, 0, negative 5, 0. As you see, we end up with a square. All sides equal and 90-degree angle between each side. So it's a square. Again, not a function, it's a relation. Here we see a parabola. However, as before, the x and y interchange their roles. So x is a value of y that is an input. This would most likely be a sideways parabola. So using table of values, let's see how this shape may look like, x and y. If y is 0, then x is 1. If y is plus or minus 1, then x would be 2. If y is plus or minus 2, then x would be 5. That's probably enough to see the shape. 1, 0 is here, 2 plus 1 or minus 1 for y, so these 2 points. And if x is 5, which is here, then we have values barely 2 or negative 2. So it looks like sideways parabola. Let's join those points. It looks like that. Still not a function. We can write at least one number on each axis, so 1 is here and 1 is there. And a cubic function, but again, the role of x and y are interchanged. So the regular cubic function looks like that. So we may expect that we'll have the same shape, but possibly sideways, either like this or like that. Well, let's see. Let's use a couple values, x and y. So if x is 1, then y is also 1. If x is negative 1, then y is negative 1. If x is 0, then y is 0. If x is 8, then y is 2. And negative 8, y must be negative 2. That's good enough to see the shape. So 1, 1 is here, negative 1, 0, 0. And this will be 5, 6, 7, 8, approximately here barely 2, and approximately here barely negative 2. So you may need to join those points. Sideways cubic function. It's flattened here. Let's place a couple numbers on the scale so we can recognize the scale. This is 1 and that's 1. The last example in this lesson is to investigate the shape of family of functions. So this equation contains a family of functions with parameter a. A is a constant, but this constant can change, and the shape of the function will change accordingly. However, the function y is really of the variable x. So x is a variable, a is a constant, except that this constant can change to produce various graphs, members of the same family. Since we play with lots of a's, it's a useful thing, especially for family of functions, to use graphing calculator and be able to produce many shapes of this family in a short time. Okay, we have our graphing calculator, if we push the button y equals, then we can plug it in the formulas. Since the formula is a cubed over x squared plus a squared, if a is equal to 1, then we are going to plug it in 1 divided by x squared plus 1 squared, which is 1. And we can graph it. Let's graph it in a standard window zoom 6. Because the graph seems to be very small, we can zoom in by pushing zoom 2 and enter. So that's a little bit bigger. Remember, the shape was with a equals 1. Now let's try a equals 2. Under the second function, 2 cubed, which is 8, or maybe let's just write down 2 cubed for now. 2 to the 3 divided by bracket x squared plus 2 squared bracket, and graph both of them. So that was the first one. The a2 gives you a little bit higher graph. Well, let's see what will happen if a would be -1. So for example, -1 divided by bracket x squared plus -1 squared is still 1. So, and graph it. Well, so the shape is upside down, but looks like similar curvity as the one for the a equals 1. We may expect that a -2 will give me this kind of shape. Well, let's try maybe 1/2 for a, just for change. So 1/2 is 0.5, and that was cubed, divided by bracket x squared plus 0.5 squared, 0.5 squared. And see this graph. It's lower, as we expected. See, this number is most likely 1/2. That one is 1, and that will be 2. Therefore, the shape is like a bell. However, the maximum height of the shape corresponds exactly to the a. So that's nice to see this family of functions, how it changes in respect to the parameter a. Okay, so let's come back to our piece of graph paper and try to record what we discovered. If a is equal to 1, then the shape was somehow like this. Bell like that. Symmetrical with the height equal 1. If a was 1/2, then the shape was the same but a lot lower, so below. It's a bell like this but below the red one. If a was 2, then it was higher like that. And we may expect that if a is, for example, 4, then the shape would go somehow like that. One more, if a was -1, then the shape flipped to the other side and it looked similarly as the red one, but flipped over with the minimum at -1. So here's the picture of our family of function. I found a nice picture of architecture here that you can see the families of functions. They change. They are steeper. The higher the roof, the steeper is this V shape here. So it's a nice piece of architecture that depicts the use of families of different shapes. They have something in common. You see the same V, but they are dilated in various ways.